Hey everyone, let's talk about some of the physical characteristics of these solutions, and they give rise to some things that we call colligative properties. So what the heck does this word colligative mean? Colligative means that we don't really care about what solids are dissolved. What we care about is how much of them is dissolved. So colligative literally means depending on the collection, aka how much of that stuff is dissolved in solution. I don't care if it's NaCl, CaCl2, what have you. We care about how many solute particles are in there, not what they are made of. So it gives rise to 4 colligative properties that we're going to take a look at today, starting with the vapor pressure of solutions being lowered. So it turns out that experimentally we know that the vapor pressure of different solutions goes down whenever we put dissolved solutes in it. So why is that? What's going on there? Well, when we add that in there, they're going to take up some space, these little solid particles, they're going to take up space near the surface of the liquid, and that prevents some of the liquid molecules from escaping into the gaseous phase. So vapor pressure is the pressure at which the liquid turns into a gas. And so if we make it hard for those molecules to do that, that in turn is measured as a lower vapor pressure. So the less vapor pressure, that means we need more energy to vaporize stuff, which you can predict what's going to happen to the the boiling point, and we will look at that a little bit later on. There is a law that helps to describe how much the vapor pressure is lowered. We are not going to get into the actual meat of the law, but Rowells Law helps us to figure out how much that vapor pressure goes down. If you go on to further study in chemistry, whether that be AP or like a college level course, you'll definitely use Rowells Law to see to what extent these different pressures are affected, and it brings in a whole lot of different stuff, including different concentrations and constants. So we're not going to go into the math just yet, but that math does exist, and it's part of this thing called Rowells Law. We can also see this graphically, and so you're used to one of these vapor pressure phase diagrams, and you'll notice on the y-axis here we have the vapor pressure increasing, and then down here on the x-axis we have the temperature. And we're used to knowing that as we increase temperature at a given pressure, let's say at 1 atm, as we increase temperature we go from solid to liquid to gas, but we've talked about earlier that we can go directly from solids to gas at different pressure and things like that. Notice what happens if we make a solution. So the initial black line that you see, the Y-shaped black line that goes kind of like this, that black line is for a normal liquid, solid, or gas. But as soon as we start dissolving stuff in it, then we get to the blue line. So the blue line is what happens if we make a solution, if we mix together, let's say, a solid and a liquid. And notice what it does, right? So it makes the solid form at a little bit of a lower temperature at a given pressure. It makes the gas form at a little bit of a higher temperature at a given pressure, and it changes pretty much everything. So as we discuss, say, the freezing point depression and the boiling point elevation later on, you can come back to this part of the video to take a look at this graph because it helps to explain a lot of that. Another piece of solutions that is important for us to discuss is osmosis. So you likely remember osmosis from biology. Osmosis is this property where if you have a semi-permeable membrane, that means you have a membrane that will allow, let's say, water molecules to go through it, but not solute molecules. The water is going to rush into areas of high concentration to basically alleviate and make the solutions on both sides of the membrane at equilibrium. So what does that look like? Well, if we have a really, really concentrated solution, we're going to see osmosis happen at a pretty high rate, right? If we have a whole lot of solute, in this case, these pink molecules here are representing the solute molecules. If we have a whole lot of those, it doesn't really matter what they are because this is colligative, then we're going to see a whole lot of water rushing in really quickly to try to alleviate that concentration gradient. Whereas if there were only 1 or 2 of those things on the left-hand side, 1 or 2 of those solute molecules, the rate would be a little bit less. So the pressure, or the rate or pressure, is a little bit lower if you have fewer molecules of solute, and it's higher if you have more, but it doesn't depend what they are. The last two colligative properties we're going to talk about is freezing point depression and boiling point elevation. So freezing point depression means that solutions actually have a lower freezing or melting point. And if you go back to the triple point graph or the vapor pressure phase diagram graph, you can see why that is for solutions. And this is pretty darn important, and it helps to describe why in the wintertime we put salt on roads. Because if we put salt on roads, the water that's in the ice and the snow mixes with the salt, makes a solution, and if the freezing point of water is normally 32 degrees Fahrenheit, and we make it a solution and it decreases, let's say down to like 0 degrees Fahrenheit, that means the roads will be covered by liquid water or a liquid solution as opposed to ice, and you have a lot better traction on liquid water than you do ice. So we don't want ice, therefore we put salt down on the roads, we make these solutions. They are going to freeze at a lower temperature, and so it can be colder outside and we still have liquid, really an aqueous solution, but we still have what appears to be a liquid on the road, which gives better traction. The opposite is true for boiling point. Boiling points actually go up. If you look over at the phase diagram, you can see this. But again, remember, this is all based on vapor pressure. So if we add solute, and that decreases the vapor pressure because it's kind of taking up room at the surface of the liquid, like we talked about at the beginning. If we have less vapor pressure, that means we need to add more energy, and energy is temperature, and so we're basically raising the temperature, raising the boiling point. That means the boiling point goes up because we have less pressure. We've talked about boiling being the point at which the pressure of your vapor pressure, overcomes the pressure of the atmosphere pushing down. And if we take this value on the left-hand side, if we take the vapor pressure and we decrease it, we're going to need more and more energy to make that vapor pressure become greater than the atmospheric pressure. So that's